Thanks. Okay. Hello, everyone. Today we are happy to host Stan. Stan is a final year PhD student at VGG in Oxford and a visiting researcher at Meta in London. During his PhD, he has interned at Google and Microsoft Research, and he completed his master's at Cambridge with distinction. His work focuses on generative models and 3D computer vision. We are looking forward to your talk, Stan. Thank you very much for accepting our invitation.
Thank you so much for the introduction. Thank you so much for having me, and thank you so much for coming to listen to the talk. Today, I'll be speaking about a paper called Bold 3D on generating 3D scenes in seconds, which is work that I've done at Google during my internship, and it was presented at the ICCV earlier this year. Let's see. In just a couple of years since the diffusion papers came out, our community has made astounding progress in generative modeling, enabling image and video generation at quality we haven't seen before, at high resolution with sounds and with really good prompt adherence. Not so long ago, Will Smith was still struggling to eat spaghetti, while today he can do so like a real gentleman, and he even uses a fork. However, despite the wonderful progress on the quality, the level of control, and the number of supported modalities, I cannot help feel a bit like this. When interacting with today's generative media, I feel kind of like a passenger on a train, where I'm merely observing a beautiful, beautiful world go by. And that can, of course, be a fascinating experience on its own. But I want to do much more. I want to step into the world and experience it in all its richness. I want to be able to interact, experience, and alter the generated media and worlds as if it was real. And I'm by no means alone in my desires. In 2022, the gaming market was around 9 times bigger than the movie market, suggesting that many of us love experiences where we can interact with the world and control the outcome. And even a game as simple as Minecraft sold over 350 million copies worldwide because it enables really rich world exploration and interaction opportunities. We can interact with the objects in the scene, other creatures, animals, other agents. We can walk around in the scene, view it from different angles, and perform a bunch of different actions. And the first step towards enabling such rich interactions is just being able to move around in the scene and observe it from different angles. And to enable such applications, my research has been focusing on transforming images to 3D so that we can do precisely that, so that we can view the scene from different angles as if we were moving inside it. A studious listener could now ask, well, if we only need to move around in the scene, would a 2D generative model be sufficient? Does the generated media actually need to be 3D, or could it just create an illusion of being 3D? And maybe it would be enough to train a video model that's conditioned on camera motion as long as it's fast enough. And on the left, I'm showing a video from Sora from 2 years ago almost, where we're moving the camera around in a scene. And first we see a market, a bunch of people, but then as we keep moving the camera, the market disappears. The camera keeps moving and the people disappear as well. Of course, back then, the videos were also generated offline. It took maybe minutes to generate a video like this, but we've made great progress since then. And in August, Genie 3 came out, where the model now runs at interactive frame rates, and the memory horizon is on the order of a couple of minutes. So the rate of progress is astounding, but we're still not quite there, because in games, interactions really need to persist over hours of gameplay. Even if the persistency was there, and I'm confident that the horizon will keep improving, the cost of running such video models is way too big for this to be viable for the public as a gaming engine. If you check the price points of Veo 3 Fast, so that's the cheaper, faster version of Veo 3.1, it costs 15 cents per second, which means that it costs $500 per hour of gameplay, where Minecraft costs $20 for a lifetime. So we're still multiple orders of magnitudes of this being a generally accessible game engine. And 3D remains the only cost-viable way to provide interactive experiences to everyday users. The problem of inferring 3D structure of the world from images is very challenging, because in case of few observations, and especially just one observation, this problem is rife with ambiguities. We have the scale ambiguity, where we don't know if we're observing small objects close to the camera or big objects far away from the camera. There is also what I loosely call projective ambiguity, where in absence of additional cues, it's impossible to tell the exact shape of the 3D object we're observing. And there is the most obvious one, the ambiguity of occlusion, where several regions of the scene can be occluded by objects that are in the scene, or some regions might just not be observed. And if we want to create these rich, high quality experiences, then our models need to be able to model the distribution of possible scenes given an input image, and they need to be able to hallucinate unobserved regions. So we really need a generative image to 3D model. Finally, I really believe it's extremely important that this generation done is in a feed-forward manner to ensure that the generation is fast and cheap. And this is for two reasons. First of all, it's likely that for long-range interactions, the world might be built or edited on the fly as the user moves in it and explores different parts of the world, or changes the state. And if we want such experience to be seamless, we need to generate the world. We need to generate the world in a feed-forward, fast manner. Secondly, we're seeing an unprecedented scale of demand for generative content creation. When GPT-4o launched, OpenAI needed to quickly limit the number of allowed generations per user because it very quickly got too expensive. And I think we're only starting to see the demand for content creation. And if we really want this to be available to everyone, the generation needs to be cheap, fast, and our methods need to be feed forward. And that's exactly what Bolt3D is. It's a feed-forward model for image to 3D generation. It takes as input any number of images, as few as one input image, and in just 6 seconds on a single GPU, it transforms it to an explicit 3D representation of 3D Gaussians, which can then be rendered in real time in a browser. Designing such a model for 3D generation of scenes is very challenging. And this comes down to two aspects of the data that we have to deal with when generating 3D scenes. First of all, the data is unstructured, where in 2D, the data is nicely organized on 2D grids. 3D scenes can be unbounded, they're unstructured, the points can be everywhere, and we haven't really even, as a community, agreed on what's the right data structure to work with 3D so that we can put it in our machine learning models. The second challenge is obviously the scale of data, where 3D data is much more scarce than 2D data. So for image generation, video generation, we have millions, maybe billions of data samples to train our data-hungry models. But in case of 3D objects, we have much fewer. And the bigger challenge, there's even a bigger challenge of the fact that there are even fewer densely annotated 3D scenes. This is why a really successful approach to 3D generation was decomposition of 3D generation into 2D generation and then distilling it into a 3D model. And that's the approach that was presented at NeurIPS last year called Cat3D, where a 2D generative model would first be trained to output a bunch of generated views, and then a somewhat traditional at this point, 3D reconstruction pipeline like a NERF would be used to distill these views into a 3D model. This resulted in really good quality because we could bootstrap off the amount of 2D data that's available, but also, importantly, we could use the data structures and the architectures that we've developed for images over decades of research. But the issue with an approach like Cat3D is that it's really costly. So if you see the time breakdown, it takes much longer to distill the 3D asset from the 2D images than to generate the 2D images. And this is because this 3D generation process is not feed-forward. It's optimization-based. We need to perform this distillation process. What's more is that this distillation process is actually under constraints for many regions in the image. So for example, if you, let me just play that video again. If you observe the background, a lot of it is blurry and not really well defined. And that's because the backgrounds are under constraints from these multiple images on this 2D sphere. Instead, Bold3D generates 3D directly and thus overcoming the optimization bottleneck. And the key idea in Bold3D is to represent the 3D scenes by two grids of 2D Gaussians. So to represent them by splatter images. And here's a bit of just a small background on what a splatter image is. It's a paper we had at CVPR 24, where the idea was to represent a 3D object by encompassing 3D Gaussians in one 3D Gaussian in each pixel of a 2D grid. And the channel of the pixel would represent the parameters of the Gaussian, the opacity, the color, the shape, and the location. And by embedding these 3D Gaussians in a 2D data structure, we could then use a traditional UNet 2D architecture to represent a 3D object. But and Splatter Image was able to surprisingly represent a large variety of objects generalized to pretty much all of observers. And even the occluded regions of the scene were fairly reasonable. But because there was only one image, in the splatter image formulation, there's only one image representing the entire object or scene. And for objects, this one image was sufficient. But for scenes, it's unlikely that we will be able to encompass the whole 3D scene in just one of these 2D grids. The bigger challenge was, the bigger problem is also the fact that splatter image used deterministic losses. So in occluded areas of the object in the backs, it was reasonable, but it was still blurry because in presence of ambiguity, the model has to regress to the conditional mean of possible solutions. And these are the problems that Bold3D solves. So first of all, to represent a scene, we will represent more splatter images than input views. So we might get as input just one image or maybe two images, but we will represent the scene by many more images and thus increasing the capacity of this representation. Secondly, these splatter images will now be generated instead of regressing, allowing high quality modeling of unobserved regions of the scene. And each of these splatter images will represent 3D Gaussians from one camera frustum. But when you put them together, when you concatenate them and use all of the Gaussians, they can represent the entire 3D scene, as you see on the right. So each of the rotating objects is one splatter image, but when you put them together, they can represent the entire 3D scene. So this is really the key idea behind the method, to generate 3D scenes by generating multiple splatter images with a diffusion model. Okay, so let's dive a little bit more. The method of generating splatter images consists of two parts. The first one is a latent diffusion model that generates multi-view images and multi-view point maps of the observed scene. These images and point maps are then passed to a Gaussian head. This is a transformer-based network that outputs the remaining properties of splatter images, which then represent the entire 3D scene. The reason why this generation process is factorized into two parts boils down to the type of data that we can reliably obtain. For color, we can get multi-view datasets. There are quite a few multi-view datasets out there. And for position, for point maps, we can run pretty robust off-the-shelf structure for motion pipelines to get dense point map annotation. But for opacities and scales, it's much more difficult to get high-quality supervision of these modalities for these pixel-aligned Gaussians. But the good news is that once we have the colors and geometry, conditional regression of the remaining parameters becomes much easier. And that's why we have this separation of two parts, the one where we can obtain the robust, high-quality data, and that part we will learn to generate directly using direct supervision with a diffusion model. But for the remaining parts, for the opacities and scales, for which is much harder to get good quality supervision, we will learn them in a kind of unsupervised way using just rendering losses. The generation process, the first part, is implementing using a multi-view latent diffusion model of appearance and geometry. The input to the model is a set of seen and unseen views of the scene. The observed views contain a clean encoded RGB latent, so that's a full resolution image that's passed through an image VAE encoder to encode it to a lower resolution RGB latent. The observed view will also obtain a random geometry latent. So at the start of the denoising process, it will be a completely noisy image. And the view will also get the camera rate coordinate telling us what is the camera pose of this conditioning view. For the target view, both the RGB and the geometry latent will both be noisy. The multi-view latent diffusion model, which is a mix of convolutional and transformer layers, will then denoise the images. And at the end of the denoising process, it will output a clean RGB image latent and a clean geometry latent. These will then be decoded with separate decoders to full resolution images and full resolution point maps. Then the second part of the model will take place, where we feed in the full resolution images and point maps, and we feed them to a multi-view Gaussian head, which is just a transformer-based network, which outputs the remaining properties, the opacities and scales of splatter images, thus completing our generation process. To train our model, we curated a large data set of 3D scenes. We ran master, a structure from motion pipeline that's at the time of working on Bolt3D, this was a recent state-of-the-art model. Of course, now we have VGGT and the follow-ups, which are likely better. But at the time, we used master, which was a structure from motion, an off-the-shelf structure from motion pipeline. And we run it on all scenes from Co3D, Real Estate 10K, MV Image, and DL3DV to obtain dense geometry annotations for all pixels and all views in every scene. In addition to that, we used a synthetic object dataset not similar to Observers. So now I get to show what Bolt3D can do and a bit of analysis on what contributes to the quality of the results that we achieved. So first, Bolt3D works on pretty much anything. It works on synthetic generated objects, real objects, indoor scenes, outdoor scenes, and it can generate different shapes of scenes. So it can generate them from these 360 trajectory, forward facing, or even fly through the rooms. It can also take as input any number of input views because the multi-view communication is based on transformer layers, and we can provide a flexible number of observed and unobserved views. And where the model receives conditioning, it adheres to the observed prompt. But if it doesn't observe any information from the conditioning images for a certain part of the scene, it will generate it. So you can see it as a sort of unified model for reconstruction and generation of 3D scenes. And finally, I began my talk with this motivation of interactive experiences. So true to my word, on the project website, we have a 3D viewer where you can go and actually explore these scenes for yourself in real time in the browser without an external GPU. Okay, so let's now just analyze how Bolt 3D contributes to the quality of the results. First, I began by explaining that previous models regress pixel-aligned Gaussians produce blurry outputs due to being regressive models. And these regressive models, for example, Fresh 3D, struggle to faithfully represent unobserved regions where our model generates plausible outputs. And this ambiguity can be due to self-occlusion or due to the camera moving outside of the camera frustum of the source image. Secondly, our choice of a generative model is a diffusion model, and we hypothesize that this is what allows us to get higher quality results than prior work that uses an adversarial framework together with a VAE. And the diffusion-based model is just much more stable for training at scale, leading to higher quality results. One really important part of Bolt 3D, and perhaps the most interesting technical point, was the design of the VAE for compressing point maps to low resolution latents for the diffusion model. So the VAE is the part of the latent diffusion model that compresses high resolution images to low resolution data for higher efficiency of computation of the diffusion model. And we found that VAEs, which were pre-trained for image autoencoding, were not appropriate for autoencoding geometry. So here at the top, I'm showing the data from our reconstructed point clouds from master. And on the bottom, I'm showing what happens when you pass the point map through the image autoencoder. So there were some works in the past that suggested that maybe image VAEs are sufficient for autoencoding depth maps. We found that to not be the case, and especially for larger scenes. So on the left, I'm showing kind of bigger room or kind of outdoor scale scenes, which pretty much just fail catastrophically when trying to autoencode them with the image VAE. And the reason is that it's just a completely different objective, autoencoding images and autoencoding point maps. We care about different perceptual qualities of the two modalities, and it's unlikely that one of them, that the image objectives will be universal for 3D objectives. More importantly, the 3D data, as I started before, is also unbounded. It can be from where images are in 0, 1, 3D data can be on much bigger scales. And if you scale it down to the 0, 1 region, the 0, 1 bounds, you lose a lot of perception, you lose a lot of precision. And in our paper, we tried a bunch of rescaling mechanisms to put them to the 0, 1 range, and pretty much none of them work. And here I'm actually showing the best one. So it's fair to say that these image VAEs generalize poorly to geometry.
Stan, can I ask something?
Yes, of course.
You know, I guess Geo4D, right? Another work from Andrea, and
that's right.
Encode point maps, and they map it to -1, 1, and they have this special loss with uncertainty. Were you aware of this? Have you tried this, or what do you think about that approach?
Yeah. I did try. That was one of the things I tried quite early on when designing this model. And so I found that, so one important part in Geo4D is the fact that they have post-processing optimization that enables them to kind of move the, maybe get rid of some artifacts that are induced by the errors. Secondly, in Geo4D, they also fine-tune the decoder. So with that was one thing that was important for Geo4D. So that kind of aligns with our findings here. And lastly, in our case, we really wanted to show a lot of 360 cases. And it is true that for when you kind of move in this forward-facing circle, maybe the errors that you see, especially in depth, aren't that big because you aren't introducing too much parallax. But if you've seen in a lot of our videos, we're showing this 360 video because that's the most challenging one, actually, because if there is a depth error, then if you see it from perpendicular angle, then you will see it. And to make that kind of really challenging angle really work, we found that training the VAE was really important. And in a second, I'll actually show that there is like one funny tweak about it.
Okay, thanks.
Yeah, but yeah, really good question. So interestingly, we found that for the decoder of a VAE for autoencoding point maps, it was really important that our VAE was a transformer-based network. So on the left, I'm showing the data. In the second column is our geometry VAE that uses a transformer as the decoder for the VAE. In the third column, I'm showing what happens with a traditional convolutional architecture, which is normally the default for autoencoders. And on the right, I'm showing the image VAE from the previous slide. And you can see in the case of a convolutional geometry VAE, this is for this model and for the second and third column, we trained on point map data. So we've tried variants where we trained from scratch or fine-tuned from an existing one. These are both trained on the same data end to end for a similar number of trajectory, a similar number of iterations with a similar number, comparable number of parameters. It's not exactly the same, but it's comparable. And nonetheless, the convolutional VAE just had a lot of these wiggly, squiggly, weird misalignment artifacts that it just, however hard I tried, it was pretty much impossible to get rid of these really visually jarring artifacts, which matter a lot if you try to optimize for novel view synthesis quality. And we hypothesized that this is due to the inherent inductive bias in the convolutional architecture, where due to this like localized receptive field, it leads some errors introduced by the sampling from the posterior distribution lead to these artifacts. And we found that a transformer-based decoder worked much better. And this was the case across outdoor scenes, indoor scenes. You see a lot of bent lines on this cabinet. This is also true for smaller scale objects. So it's less pronounced. The difference is not that big, but it's still observable and not quite at the quality that we would like it to be. So having a transformer-based decoder was really important for the performance. And there are a bunch of different standard geometry losses that we use for training this end-to-end that we show in the paper. That all of that was really important for high quality 3D scene generation. At the start, I also started by saying that an optimization-based pipeline might work really well. And it's important to compare to that pipeline, even though our method is a completely different setup in which we're performing this one-shot sort of feed-forward 3D generation, and the model has to just guess the answer without any optimization. And on the left, I'm showing a video from CAD3D. On the right is our reconstructed model. And on the right, you see the metrics. And Bolt3D is not as good in quality as CAD3D. It falls by maybe 1 or 2 PSNR, but it's much, much more efficient. So by running a feed-forward model instead of an optimization-based one, we reduce the inference cost by 300 times and still get really good quality of the 3D scenes that we generate. Finally, I'd like to be very honest and discuss the limitations of Bolt3D because there are obviously some. First of all, something that I glossed over is how we specify the target camera poses. And we build on similar heuristics similar to prior works, for example, CAD3D, where if we want a 360 scene, then we will place our cameras on a sphere on kind of these 2 circles. But we observe that our camera placement, for example, the up vector or the scene scale can significantly affect the reconstruction quality. And sometimes you need a small hyperparameter search to find a good up vector and upscale if you don't know it a priori. This could be probably ameliorated by better data augmentation during training time, but that's the limitation of the model as is. Secondly, the model does not work super well on transparent and reflective surfaces. And this is due to 2 reasons. The first one is those are the regions where structure from motion typically struggles, and that's how we obtained our data. So the generative model inherits the limitations of the structure from motion pipelines that we used for obtaining the data. And secondly, learning these reflection capabilities and transparencies is actually fairly difficult for feed-forward 3D Gaussian models. So optimization-based 3D Gaussians can represent refractive and transparent surfaces, but it seems to be, for some reason, quite hard to learn them with feed-forward 3D Gaussians. And finally, the model struggles with thin structures, especially on the plans. And this, again, boils down to the limitations of and challenges in the structure for motion pipeline that we use to obtain the data. That being said, I think we made great progress in 3D scene generation with Bold 3D, and I'm excited about different ways in which it could be extended. So in the future, I think it would be awesome to enable more interesting interactions. So in these scenes, we're able to now walk around in the scene and just observe it, but it would be really fun if we could start including some dynamics. So maybe there are some animals moving, other people moving, maybe we can open a door. That would be really exciting. Secondly, I'd love to be able to move from generating a scene, this like kind of medium scale room scene, to really large scenes. So generating entire cities, entire houses. And finally, one direction that I'm personally really excited about is, now that we've generated an explicitly 3D asset, can we actually put it in a physics simulation? So that's one advantage. Another advantage of generating explicitly 3D representations is that maybe we can mesh them or attribute some physical properties to them to put them in a physics-based simulation for training embodied agents. And this would enable a bunch of capabilities that I'm really excited about the future. So on high level, I think in my mind, 3D, despite the progress on 2D diffusion models, I think 3D remains still the only cost-viable way to provide users with interactive experiences. Because with these explicit 3D representations like 3D Gaussians, you can just drop them off, ship them off to the user, and they can view it in a browser without using a GPU anymore. And if you really want to give it to so many users, like millions of users on the planet, then that's probably the best economically viable option. And in Bold 3D, the idea was to do that by organizing the 3D data as 2D splatter images, which then enables building on a scalable architecture and a lot of data. And one key important message in Bold 3D was training the VE with a transformer-based decoder was really important for performance. And with that, I'll finish the talk. And thank you so much for listening. I would love to hear any questions. Yeah.
Thanks a lot, Stan, for this amazing talk and really nice looking results.
Thank you.